What about recent climate change? What can we say about its causes? Here, once again, from the instrumental record is global mean temperature relative to its long-term average. This is annual means given by the blue dots. The red curve is a 5-year running average. As we talked about before, the temperature was fairly stable until the early 20th century. It started to go up. It leveled off in mid-century and started to go up again in the late 1970s. We can also measure things like the carbon dioxide concentration of the atmosphere. We have measured it directly from Hawaii since about 1958, but we can also figure out what it was by analyzing the composition of minute bubbles of air trapped in ice cores. That's what you see by these different colored dots in this diagram going back to the year 1750. The lower diagram shows an estimate of carbon flux into the atmosphere from fossil fuels and other sources. Together, these diagrams paint a picture of ever-increasing carbon dioxide, starting at about 280 parts per million by volume in the pre-industrial era and rising to 370 by the year 2000. At the time I'm making this recording, in the middle of the year 2013, we have just passed 400 parts per million by volume. But greenhouse gases aren't the only things that's changing in the atmosphere. Combustion of fossil fuels, land clearing, and so forth also contribute to atmospheric aerosols. And here is a record of global anthropogenic emissions of sulfur, mostly from burning of fossil fuels, going back to 1850. The emissions of sulfates produce aerosol particles which largely reflect sunlight. This has actually been a cooling influence. The sulfate emissions leveled off, though, between about 1975 and 2000. Besides man, nature itself produces very large climate forcing. Not only do we have orbital variations, but on shorter time scales, we have things like volcanic eruptions. Here's a graph going back to 1860 showing two different estimates of the aerosol optical depth, which is a measure of how much sunlight is absorbed and reflected by aerosols, from volcanoes. Each of these spikes corresponds to a major volcanic eruption. Volcanic eruptions are chaotic in time. They're not very predictable. They're not predictable at all. But you can see that by statistical accident, for example, we had no major volcanic eruptions between about 1915 and about 1960. By running climate models, we can start to make attributions of climate changes, at least over the last 100 years. This is a graph that we'll discuss in detail in the course, showing the observed and modeled change in atmospheric temperature over the last 100 years. And at least for the model, we can break down that temperature change into different contributions. So these different colored lines show 5 different contributions, 2 of which are completely natural, changing solar output and volcanic activity, and 3 of which, ozone, greenhouse gases, and sulfate, are largely anthropogenic effects. But they work in some cases in opposite directions. So sulfate actually contributes to a cooling. Sulfate aerosols, greenhouse gases, contribute to an increase. The distribution of temperature increase around the world over the last 100 years is far from uniform. This is a map based on instrumental records showing the change in temperature between the early 20th century and the first decade of the 21st century. Global warming is not globally uniform. A lot of the warming occurs over continents in the northern hemisphere. There are places like the far North Atlantic and the southeastern part of the United States which have actually been cooling over this period of time. What accounts for the non-uniformity of the change in temperature in response to presumably global forcing?